So now moving on into the nodal analysis further, there is this one more concept that you need to know, which is the super node. So in all the examples we have done so far, we have not included a voltage source in the circuit. Now, the first thing is, why does a voltage source make it difficult to use nodal analysis? Yeah, I won't call it difficult, it just makes it a little different. Because as I've mentioned in the voltage in the sources video before, that the main characteristic of a voltage source is that the current through it can be anything. It could be 0 amps, it could be 1, it could be 2 amps, it could be 3 amps, or anything. So when you're applying KCL on a node and there is a voltage source connected right besides it, you do not know the current coming into the node, so you have to find another way. So for this, the concept of super node comes in. So I just demonstrate how you can actually apply nodal analysis despite a voltage source in this example. So now let's see what the concept of supernode is through this example. So the first thing in this circuit is we just identify all the nodes, and I've just identified all the nodes. And now let's start off by identifying the reference node, and I'll just call D as the reference node. So I can actually identify any node as the reference node, as I've mentioned in the previous examples too. It depends on me and it won't affect the answer in any way. So as D is the reference node in this case, I'll just write VD as 0 volt and the others are unknown. So the first thing is, let's write the KCL at A. So clearly there is this 5 amps current entering, so I write plus 5. There is this current entering from here and this is coming from node C clearly, so I write VC minus VA divided by 4, and then there is other current coming from B, so I write VB minus VA divided by 3 is equal to 0. So this is pretty simple and this is what we have done so far. But now a problem comes. If I start writing the nodal equation at the next node, which is B, I can see that there is this branch coming, but I do not know what the current is here. So that would pose a problem because I need to know the current when I'm applying the KCL. The same way, if I apply the KCL at node C, I do not know the current coming from this branch because there is a voltage source, and the current through a voltage source can be anything. So I'll just say that the voltage source 2 volt, but still the current can be anything. So the concept of supernode states that if you combine these two nodes and you write a KCL in a way that actually composes of all the branches coming into these two nodes separately. For example, this branch and this branch coming into node C, this branch coming into node C, and I guess that's it. So, and if you just combine the KCLs, it won't have any effect on the answer, and that is pretty logical too, because if you look here, and I'll just clean this up. If you look here, if there's a current of I going to B, because from the voltage source, so the same current but in the opposite direction is going to C2. But if you just add them up, that would mean plus I minus I, and that makes it 0. So if you add the KCLs of both of these nodes, then you won't have an effect on the overall KCL. So I'll just write a KCL on super node. We'll just call it super node BC because it combines the nodes B and C, and we'll just write the KCL now to see how it works. So there is this one current coming from here from node A, so I write VA minus VB divided by 3, and then there is this one current coming to C here, so and that's coming from VA, so VA minus VC divided by 4, and then there is this last branch here, so which is coming from VD, so VD minus VC divided by 2, and this is equal to 0. So these are the two equations. So all I did was I just wrote all the currents coming into B and C except for this one branch. I just omitted it. So this brings out these two equations. So if you look at it, there are three unknowns, VA, VC, and VB, and there are just two equations, so this is mathematically unsolvable. But thankfully there is this one other thing in the supernode concept, which is that you can always form one other equation in a supernode, and that is clearly VC is at the positive terminal of the voltage source and VB is at the negative terminal of the voltage source. So the two nodes that actually have the voltage source in between, you can just write their difference, and that is equal to the voltage. So because the voltage source actually tells you that the voltage difference between VC and VB is 2 volts. So this is our third equation, and now we have three unknowns and three equations, and now we can easily solve this. So I just show another example which would make things more clear now. So now I have this circuit, and I'll just initially mark out all the nodes here. So this is node A, the first node. There is this node B, and then I have this last node called node C, and I'll just choose this as the reference node VC. So V is an unknown, VB is an unknown, and VC is 0 volts because I've chosen it as a reference node. So the first thing is to make a super node because there is clearly a voltage source present. So the two nodes that actually compose the voltage source are VA and VC. So I'll just combine these two and form a a super node. So I'll now write a KCL at super node AB, and I'll start off by writing all the branches coming into A. So there is this 4 amps current, so there is plus 4. There is this one other current coming from this branch, and that is VC minus VA because that's coming from VC, the node C, over 1 by 2. And I'll just omit this one because that is the voltage source. And there is this one other current coming from node B, so VB minus VA divided by 1 by 3. Everything is just the same. And now let's all I guess these are the branches that are into A. And now let's move on to the other node in the super node. So there is this one current coming from A, so that is VA minus VB divided by 1 by 3. And then there is this one current coming from node C, so it is VB divided by 1 by 6. And then there is this last current coming from here, so that is plus 9 0 to 0, and I omit this current because it's clearly coming from the voltage source. So these are all the currents coming into the super node, and here we have an equation. And but we have two unknowns here, VA and VB, because VC is 0, and so we need another equation. And in the super node we can always form an equation. So node A is at the positive terminal and node B is at the negative terminal. So I'll just write this is equal to 5 volts, which is the value of the voltage source. So now I have two equations and two unknowns, and now I can easily solve this question and find all the nodal voltages. So this is how the concept of super node works. So I'll just show another example in which I actually choose a reference node in a way that it consists of the voltage source. So let's see what happens then. So now I have this question, and the first step is I'll just identify all the nodes. So there is this one node, node A, there is this other node, node B, there's this node C, node D, and then there's a fifth node, node E. So I'll just choose C as the reference node because it seems like it has the most branches connected to it. So and VC is 0, and VD I don't know, VE I don't know. Now I'll form super nodes that have the voltage source. So there is a voltage source between A and C, so I'll just combine these two, and there is a voltage source between D and E, so I'll combine these two. So the first thing which actually comes in our favor is that whenever the reference node is included in the super node, you do not have to write the KCL for that, and I'll tell you why. Because you cannot write the rule is that whenever you're applying the nodal analysis, you do not ever write the KCL at the reference node. So this is the first thing. And the second thing is, because we know VC is at the reference, and we also know VC minus VA is equal to 12 because the positive terminal is at C and the negative terminal is at A, and we know VC is 0, so we can just say VA is minus 12 volts, and that's that. So you do not have to write the KCL on this super node. So we're left with B and the super node E and D. So I'll just write the KCL at B first. So there is this one current coming from here, which is coming from VA. So I'll write VA minus VB divided by 0.5. There is this 14 amps current coming into here, and there is this last current coming from node D. So that is D minus VB divided by 2. So this is the KCL at node B. So now I'll write the KCL at super node DE, and I'll just clean this up. So the KCL at node DE, there is this one current coming here from B. There is this one current coming here from C. So I'll just start off. So VB minus VD divided by 2, and then there's this one current, so plus VC minus VD divided by I'm sorry, this is something wrong. We already know the current here, so that is 0.5 Vx. And now we won't count this branch because it contains the voltage source, so we move on to the next node in the super node E, because we have already written the KCL at node B for all branches except the voltage source. So for E, there is this one current coming from here, so I can just write VA minus VE divided by 2.5, and the last current is coming from here from C, so that is VC minus VE divided by 1, and that is equal to 0. So these are the equations, and there is this one more equation now which I'll write here because there's a supernode here. So VD, V, because it's connected to a positive terminal, VD minus VE is equal to 0.2 Vy. This is what you always do for the supernode. And so now, right now, I have 1, 2, I'm sorry, Va is not an unknown. I've already found it to be minus 12 volts. I have 1, 2, and there's this third unknown, and there is this fourth unknown, and there is this fifth unknown. So this is a problem. I have 5 unknowns, and I've just got 3 equations, so I need 2 more equations. But as we've already studied in the nodal analysis examples, I do have 2 more equations for Vy and for Vx. Vy is clearly Ve minus Va, because Ve is connected to the positive terminal and Va is connected to the negative terminal. And I also have an equation for Vx, which is Vb, because it is connected to the positive terminal, and minus Va. So Vx is equal to Vb minus Va. So now I have 1, 2, 3, 4, and 5 equations, and I have 5 unknowns, so I can use some concepts from linear algebra like Cramer's rule to find all of these unknowns, and hence the circuit will be solved. So this is how you apply the nodal analysis when there are voltage sources involved. So in a crux, what you need to know is that whenever you are applying nodal analysis and there are voltage sources involved, the first thing is just identify all the nodes, and then after choosing the reference node, just start off by forming the supernodes. If your supernode consists of the reference node, like in this case, you just write a simple equation and no KCL for that. So there is no KCL for the supernode that consists the reference node, and for the other supernodes that do not have the reference node, you do write a KCL, but the KCL is in a way that it combines both nodes and it does not include the branch of the voltage source. So this is what you omit from that KCL. So you just combine the KCL of the 2 nodes that are in the supernode if they are not the reference nodes. So these are the 2 things. And the third thing that you always need to remember is that for dependent sources, you can always form equations related to the nodes for the constants that they are dependent on. So for example, in this case, Vx was Vb minus Va, or Vy was Ve minus Va. So I've just made a mess of this whole example, but this is the main crux of the supernode and how it works. I hope you understand.